I'll then talk about machine learning with neural networks. And in the context of this class, neural networks and deep learning are really going to be more or less synonyms. There are differences there. There are neural networks that are, I guess, not considered deep learning. But really, these two classes of techniques have more or less been kind of, they are lumped together at this point. And so I will use those terms more or less interchangeably here. And so we'll talk about why we want to use neural networks as opposed to other architectures and what benefits they might have. And then I'll talk about how we go about actually training these neural networks. Before I jump into that, though, I wanted to mention a few things. I'm sure it's on everyone's mind, so I wanted to talk a little bit about the midterm. The midterm, as everyone knows, is next Monday. Hopefully everyone knows that. The format, there was a question about this. There's going to be 4 to 5 short answer questions. So these, short answer can mean whatever you want it to mean, really, but it's 4 or 5 questions that aim to take about 15 to 20 minutes each. So that's the goal. And there is partial credit, so if you just sort of start working through one of the solutions, even if you don't quite get the full answer, you will still get some credit for that. So the goal is to sort of demonstrate what you've learned so far. And I guess it's up, Ariel said it was up till last lecture, so it won't include the material from today. So you don't have to scramble to remember all the math we're going to show you right now, or maybe at the end of the class. But it will involve up to learning theory yesterday. It'll be a completely closed book. That's largely just due to the sort of space constraints and the fact that it's kind of hard to have open book tests with people right next to each other. But it also means we have to make questions a little bit easier so that you can, in fact, answer them without being open book. And we're going to release a practice midterm either today or tomorrow. Hopefully today, but if not today, then tomorrow. Any questions about this? Neither Ariel or I will be here for the midterm, so TAs are going to proctor it. We're actually both traveling next Monday. But the TAs will be able to answer questions during the exam. And we'll make sure all the questions, they have our number. If they need to call us really, really urgently to ask a question about it, they can always call us. But we don't expect that to happen. OK, any questions? OK. So let's talk a little bit about the history of deep learning. As by any measure, deep learning is kind of the field that is probably the hottest topic of AI right now, right? It is sort of what you hear about when you hear about all these recent advances. Every day there seems to be a new paper, a new model that's getting superhuman performance, or at least really good performance compared to humans, and kind of achieving some miraculous results, or seemingly miraculous results for a computer algorithm. So I want to talk a little bit about what's happened, and then I'll actually come back to that after I've described what neural networks are. I'll come back to that then and kind of give a more technical view of why this seems to be all happening right now. But first, a little bit of history. So, and I like this graph. It's actually a few years old now that I made this plot, but I like it because it kind of sums up both very recent history. It sort of highlights the fact that it's a very recent phenomenon, this explosion in deep learning. And it also I can track kind of where my academic career actually happened on this, because this is all very recent things. I'm actually, I have to say, I have not until recently actually started to work in earnest on deep learning. It was kind of tangential. I worked on related things. But about a year and a half ago now, my group started working on some machine learning or deep learning elements. And I think it's about half the research we do in my group now is on deep learning techniques. So they're really they're a great area to play with, because both they get amazing results and there's so much uncharted ground that there's a lot of things you can do. So there's really a very fertile area for research. But anyway, let's take it back a little further than that and come to before I was involved in the field, which is actually after this graph ends. But during the idea of neural networks goes back really very, very far to some of the beginnings of AI. So one of the first learning algorithms was called the perceptron, which is kind of a single layer neural network, very similar actually to sort of the other techniques we've seen so far, like linear classifiers, like logistic regression or a support vector machine. But soon after perceptrons kind of, and actually this is even more ancient history, but soon after perceptrons were proposed, they kind of got shut down by the proponents of more logically based AI systems. But then in the 80s and early 90s, they kind of saw a resurgence again. And this happened because the technique of backpropagation for training these networks was popularized within the machine learning community. It actually goes, the technique of backpropagation in various forms has existed much before it was ever used in AI. But it really sort of was with this kind of takeoff of this backpropagation algorithm that neural networks first got a foothold within the AI community. And this happened really in the mid 80s to early 90s as it started to happen. And then after a while, there was a kind of a lull in their enthusiasm, right? So in the early 90s, techniques like support vector machines and boosting, which we don't actually talk about boosting here, but it's another very popular machine learning technique. These kind of really rose to prominence at the detriment of neural networks. So neural networks kind of fell out of favor, and you can see there's a little lull in the, I didn't actually describe what this graph is. It's a little lull in the publishing. So what this graph is, I apologize for that. What this graph shows is I did a Google Scholar search for the number of papers that include the word machine learning in the title versus the number of papers that include the word neural network in the title, which is obviously a very imperfect metric because most of my papers, even if they're in machine learning, don't say machine learning in the title. But so it's very imperfect, but it actually corresponds pretty well to their relative popularity over time. So that's what this graph is showing here. So if it's a 1, there would be an equal number of neural network and machine learning papers, but it's probably actually past 1 at this point, to be honest. But throughout this whole graph, at least, it's showing less than 1. So there's more papers that say machine learning than there are that say neural network. So anyway, in the mid-90s, sort of the popularity of things kind of starts to tail off. And part of the reason for that is that neural networks, as we will see, form non-convex optimization problems, meaning we can't find the globally optimal solution, meaning there isn't actually that much we can say about what they're going to do, how well they're going to perform at their optimum. We can say a lot more rigorous things about convex models. So things like support vector machines or other similar models, we can give very rigorous guarantees about. But neural networks are very hard to give such guarantees about. In fact, still, the theory of neural networks is very poorly developed compared to the theory of other machine learning techniques. And in the 90s, at least, it certainly was the case that they didn't necessarily perform any better than techniques like support vector machines or boosting. And so it seemed kind of like an obvious choice, right? If they work not as well or marginally, they're very, very marginally better or very, very marginally worse, and you can't really analyze them at all, it's kind of very natural for them to fall out of favor and not be, be the primary dominant things. So then in the sort of and that kind of stayed for a while. In fact, when I entered the sort of field, the academic field in 2003, that's when my first paper was. And when the time that I entered, neural networks were kind of a dirty word, right? Like AI was too, by the way, for a while. Like you wouldn't want to mention that you do AI because it sounds like, fanciful stuff here. And neural network was the same way. You wouldn't want to mention you work in neural networks because it was sort of seen as not really where the real machine learning is. But then in 2006, and this was sort of driven by a few people, namely Geoff Hinton and some collaborators, sort of a very famous machine learning person from University of Toronto, but now also at Google. He and others published these papers on methods that they called unsupervised pre-training. So this was a technique where you would actually initialize the weights of these networks, which are very hard to sort of train and were kind of difficult to get right. You would initialize them based upon an unsupervised learning procedure. And that actually kind of spurred a lot of more interest in these techniques. Now, kind of ironically, it's sort of the common knowledge now that unsupervised pre-training does not really help these things. It isn't actually that useful, so no one does it anymore. But these ideas of unsupervised pre-training actually really contributed to the rise, again, of deep learning techniques. And then in 2012, also some work by Geoff Hinton, but Geoff Hinton and his students, called the AlexNet paper. It's published in 2012. It has something like, I haven't checked last, but it's probably over 5,000 citations. It was sort of this amazing seminal paper. what they did, and I'll show some results of this in a second, what they did was they built a neural network architecture to classify images as part of a contest called the ImageNet Computer Vision Contest. Now, before this, the techniques that had won this contest were largely sort of hand-tuned, very specialized computer vision techniques that use specialized features for computer vision to try to classify images as one of, I think, 1,000 different classes. And this paper, which we'll talk about more about in a second, essentially used kind of a pure neural network approach, and it improved upon the next best classifier by something like 26%, which was kind of an unheard of margin for these things. Usually you get, like a couple percent improvement as a major story for something as well studied as computer vision. And so this paper really kind of shocked everyone into realizing the potential of these neural network architectures, and the rise since then has kind of been really kind of amazing to behold. Some of the things that have happened are things like Facebook has started an AI research team, which is really just a deep learning research team. Google bought DeepMind for a really small company with no product. They bought them for $400 million or so. And at the time, people kind of laughed. That was a silly investment, but it's probably actually paid off pretty well. I mean, DeepMind has generated a lot of, with their AlphaGo and similar things, it generated a lot of interest. So there really has been this surge of both academic and industry interest in this area that I think really speaks to just how impressive a lot of the results that are coming out seem to be. So let me highlight a few of those then. So let me start with this AlexNet paper. Are there any questions? Feel free to jump in at any point in this. This is just sort of background history. By the way, the image there is clipped. That's actually how the image appears in the actual paper. They clipped it off to fit more room in the paper so they could do it. It's one of the most famous clipped, cut off images in any paper that I know of. But anyway, AlexNet was what's called a convolutional neural network, which we'll talk about in 2 classes from now. But it essentially is more or less just from start to finish, you take the input image, you run a bunch of linear operators followed by nonlinear functions, which we'll describe as what a neural network is. And then out comes a vector in 1,000 dimensions that says what probability each of these 1,000 classes is. As I said, it won this ImageNet competition. It was actually much better improvement than that. It won with a 15.3% error rate. This is actually, for those that care, this is a top 5 error rate. So you can make 5 guesses, and if any of their 5 guesses are right, you get a point. Otherwise, you get it wrong. It had a top 5 error rate of 15.3%, whereas the next best one, based upon non-neural network techniques, was 26.1. So improvements like that really were unheard of at the time. Since then, it's come down to about 3%, I believe, is the current best accuracy, though it's sort of asymptoted out in that people think this is not even a relevant problem anymore because we kind of reached human level performance where the mistakes that they make are kind of ones a human might make as well. So this is what it looks like. Let's take a look at a few of these classifications. And it's really kind of amazing just how many things it kind of get right. So it sees that picture on the left there. Again, all it sees are the pixels. There's nothing about the picture other than just the raw pixels, RGB values. And it says correctly it's a mite. The middle, it says container ship, motor scooter, etc. Even the mistakes it makes, like this one, is actually a cherry because there's cherries in the foreground, and it says it's Dalmatian, which I think is a very natural mistake to make. And then the second ones are things like grapes and elderberries. So it actually thinks that they are. It even saw the fruit as well as a Dalmatian, but it didn't quite get the fact that it's a cherry. And then things like this is actually a Madagascar cat, but it thought it was a squirrel monkey, and I wouldn't have known that either, right? So it's really pretty incredible that you can take just raw images like this. People have been trying to do this for a very, very long time. And really, while we were certainly making improvements in kind of hand-tuned image features and things like this, progress really was not that rapid. And all of a sudden, over the past 5 years, and this really is very, very recent, our abilities here have kind of exploded. And this is due to these techniques from deep learning. Another one you might have seen, which actually Ariel talked about in the first lecture on the progress of AI as a whole, is this program AlphaGo, which last year beat the world, not the world champion, at least one of the leading players in the whole world, the leading Go players in the whole world. It beat him 4-1. And again, using techniques that, while a little bit more complicated, actually were very similar in a lot of ways to the image recognition. So they would use a convolutional structure, which again we'll talk about what that means in a second, or not this lecture, but a few lectures from now. A convolutional structure to make predictions about what states of this Go board you should put a piece on. Even though the actual number of places you could put a piece is very large, that means a classic like search technique for searching a game tree would be very inefficient. So they use actually kind of black box machine learning and deep learning techniques to try to predict both where a person should move and whether or not you were ahead or behind in that game. So, and there are many, many more examples. You've probably heard of some yourself. There's a lot of image apps now have these filters you can run that make an image look like a painting, right? That's also based upon deep learning techniques. It's really kind of amazing just how much these have spread in the past 5 years, because it really was 5 years ago that AlexNet happened. Before then, no one was doing these things. So sort of a big question that you might have in mind is why is this happening right now? And I'll try to give an answer to that, not now because I wanted to first define what these things are, but later on I'll try to give an answer as to why this is all happening right now. Were we just not trying the right algorithms, or were we just not smart enough to figure out how to actually run these things? Or has something actually changed that makes these things possible where it wasn't possible before? So I'll answer this in a second, why I think it's happening right now. But before we do that, let me actually define what a neural network is and what the architecture is that we're actually talking about here. Any questions before I move on, though? Okay. Let's talk about neural networks for machine learning. So remember, we talked about machine learning last time, or 2 times ago. But the point I want to emphasize, and I come back to this point whenever I talk about machine learning, is the machine learning algorithms really involve 3 things. They involve a hypothesis class, a loss function. Hypothesis class is, what class of functions are we searching over? Loss function is how do we measure how good one of these functions is? And the optimization routine, which is how do we find in this whole class of problems how we actually pick the hypothesis class. And actually, this should also, I talked about a bunch of ways of doing this in the context of like linear classifiers and things like support vector machines or logistic regression. But actually, even the example we had last lecture with finding rectangles, that was also the same kind of framework, right? Our hypothesis class was rectangles. Our loss function, which is the number of mistakes we make, and our optimization routine was essentially, well, you pick the smallest enclosing rectangle of the ones that fit the positive class. So even that one had the same form, even though it's sort of formulated in kind of a different way. Now, the term neural network is really, what it really is talking about is just the first of these 3 elements. What it means is a particular form of hypothesis function that involves composed nonlinear functions in a way that I'll describe what that actually means much more detail in a second. But the important point here is that we're really talking about one of these 3 elements is what a neural network is. It is a class of hypothesis functions over which we search. You can theoretically then use any loss function, and people do use different loss functions. If you have, for example, a regression versus a classification task, you can do both with neural networks. You have to just use a different loss function. And you could also, in theory, use different optimization techniques. And people do use different variants of optimization techniques. But really, there are some ones that are more common than others. So in particular, virtually all optimization involves gradient descent techniques, or actually a slight variation on that, which we'll talk about, called stochastic gradient descent techniques. And that's really though there are some variants on this, that's the main algorithm people use to actually solve or optimize neural networks. But in theory, it's really just the first one that makes it a neural network. Okay, so let me sort of jump right in now and talk about what these functions actually are. So the way I'm going to do that is I'm going to start with just linear function classes, right? Which was kind of our starting point before. So when we talked about linear regression and logistic regression and support vector machines, for the most part, we were talking about linear function classes. In other words, h theta of x is just equal to theta transpose times x. Right? And as we saw, those could actually work quite well in some cases. But it turns out, and this is still true to a certain extent, even with deep learning in a lot of domains, but certainly before neural networks really came to prominence, the performance of machine learning techniques would really vary critically based upon the features that we pick. These are our input features. They are kind of defined outside the algorithm. And we can use things like polynomials, right? There are a bunch of other ones that are kind of general purpose features as well. Or there actually a lot of domains have specialized features. So for example, in computer vision, the raw pixels are not a great feature for images because they don't really describe what's in the image. But people had developed a lot of sort of transformations of images that result in features that a machine learning algorithm could then use. So the key point here is that the performance of machine learning depends oftentimes crucially on how you represent your input in terms of its features, especially in the case of linear hypothesis classes. So, you know, if you choose a fifth order polynomial, you get very different performance than if you choose a first order polynomial. And so this is sort of all well and good, but it kind of begs the question, right? If we're using really, you know, kind of advanced optimization techniques, or at least seemingly advanced optimization techniques to find this hypothesis class once we defined our features, why can't we just apply machine learning to learn the features themselves, right? Why don't we just learn what the features should be somehow? I won't say how yet. Let's just learn those features. Let's just, you know, give the algorithm the raw input, the actual just temperature, not squared or to the fourth or anything. Just give it the temperature and have it learn, you know, the degree of the polynomial or any other feature that actually gives good performance on our task. And so the key question, I think, is can we come up with an algorithm that automatically learns the inputs, the features from kind of the raw input to our algorithm? So let me offer one way we might go about doing that. So I'm going to now call our features, actually this is just on this one slide, but you know, just to differentiate things a little bit, I'll call our features now phi of x instead of just x. Those are our features. That's actually a very common notation, but I won't use it for the majority of this class. So I'm going to define a different hypothesis class, which is not just a linear function. It's a more complex function now. In particular, I'm going to compose together two different linear functions. So the first linear function is going to kind of define my features, and the second one will be my classifier that I'm going to apply to the data. So my hypothesis class is going to be equal to W2 times W1 times x plus B1 plus B2. Okay, so let me define what all these terms are. So W1 is the term that multiplies the input. So this is actually going to be, and we assume our inputs x here are still in R to the n, right? Still n-dimensional inputs. And these now you can think of as more just the raw inputs, like the raw temperature, not the temperature squared or anything like that. It's just the raw inputs to the algorithm. So this matrix here is a k, am I using k there? Yeah, a k by n matrix. So that takes our input, which is in Rn, and transforms it to an input in Rk, which could be either bigger or smaller depending on how we want to do this, right? And then this term here is going to be a bias term, which is also going to be in Rk to make the math work out. And here all I'm doing is I'm separately, but you know, before we bundled in this intercept term into the input itself, because I'm talking about kind of raw inputs now, I'm actually going to remove that intercept term and make it explicit in my model. So don't worry about that. It's just exactly the same as before. This is a linear function. It's just that instead of having a 1 always in my feature vector, I'm going to just put that in the you know, I'm going to make a bias term explicit here in the model. Okay. All right, so after I've done this, I've now, this whole thing here, of course, is itself a vector in Rk. So I've transformed via a linear transform, I've transformed my inputs from Rn to Rk. And you know, this is now a different space. It's kind of like a feature space, right? This is a set of features, linear features in this case, but a set of features that represent my data now. And now when I have this, I'm going to then apply another linear classifier on top of it to actually classify my data or perform regression on my data. So this matrix here, I actually want real valued outputs. So this matrix here is going to be it's going to be a row vector 1 by k, and this is just going to be a real valued number. And that's going to be how I do this composed multiplication, and that's going to be how I compute my hypothesis function. Is that clear to everyone what I'm doing there?
How do you choose the number of features?
As many as you want. Just choose k to be whatever you want. I'm also going to make one thing that it's looks a little confusing at first, but I'm just going to stick with this notation. I'm going to take theta now to be my vector, or not my vector, but really my set of all parameters. So in this model, the parameters of the model are really the matrices W1, W2, B1, and B2. But I'm just going to call theta the set of all those things, right? So when I write H sub theta of x, I really mean H sub W1, W2, B1, B2, but it's just easier to write theta. Think of it as the set of all the parameters we have. Yeah. Let's hold on. So I mean, it seems like a reasonable thing to do, right? We're going to have a linear transform, and so we're going to modify our feature. We're going to have one classifier that predicts our features, the next one that classifies our data. So I'm going to have a poll now. So suppose I run two machine learning algorithms. The first one with this hypothesis class, and the next one with just a normal linear hypothesis function, right? So the first one's going to be a hypothesis function where I have this composed nonlinear, so it's a composed set of linear functions. The second one I have a single linear classifier, which actually is just going to be, you can think of that W3 as just a row vector. So really it's just as we had before in H tilde, we have just basically theta transpose times x. So now, suppose, does everyone get this set up here, what these two different classifiers are? So one is this modified, first learn my features, then learn the classifier. And the second one is just learn a linear classifier, period. So if I do this, what's going to happen to my function? So suppose I do this, and suppose I train my machine learning algorithm now on both these two frameworks using the same loss function. And suppose even I can find the optimal solution. That's actually not possible in this first model, because that function is not convex jointly in all my variables. So you actually cannot find the global optimal solution in general of functions like that have multiple parameters multiplied by each other. But suppose I do find the global optimal solution, and suppose it's even unique. So maybe I add a little regularization term to all these things or something like that to make it a little bit unique. I shouldn't say that. So just suppose that we don't worry about uniqueness of the solution. Now, what's going to happen here? So again, H here involves many more parameters, but it has this composed form. And so the question is, what's going to happen here? Will H achieve lower training loss, but then higher validation loss? So on our training set, it works a little better. We can fit the data better, but it performs worse on the validation set. Will it perform better on the training and validation set? Will the H tilde, the purely linear one, perform better on both sets? I guess I don't have the option of that working better on the training set and the other one on the validation set. You know that's not the answer. The other possibility is that they both perform identically. And the last one is the performance depends on the choice of data or the loss function. So maybe it works better, maybe it works worse. It all depends on the data and which loss function we choose. So let me just bring that up. Oops. Why is this not? Oh, I see. Leave it up while I do this, but. examples open now. All right, we'll give it everyone 1 more minute. All right, make your final options now if you haven't yet. Everyone good? No one's having connectivity issues or anything like that? Okay. All right, so take a look at what people said. So a good plurality, at least, and a majority around the correct answer. So that's correct. They both perform identically, and so the point, I mean, this is actually what was said before. The point is actually that these two classes of hypothesis functions, though they look very different, actually end up being the same. And the reason for this is actually very simple. All I have to do here to see this is just multiply these things together. So I can write this whole thing as W2, W1 times X plus W2 times B1 plus B2, right? And so I can just call this thing here, this is just going to be a matrix. It's also in R of 1 by K. And I can just call this thing like W tilde, right, times X. And I call this thing B tilde. And so even though it seems like I have a lot of parameters, more parameters here, the actual expressiveness of this function is exactly the same as my purely linear function. And so that's why, even though you have more parameters, and it seems like maybe I'll be able to learn features that describe what I want, it turns out that you can't do that with these linear classes because things just don't actually give you any more representational power. So where does that leave us? Well, fortunately, there's a very simple alternative that we have, which is just to take this same architecture but add nonlinear functions after each linear operation. Right? So in particular, we can do something like this. So I'm going to use a different board, but I'm going to take this hypothesis function. No, sort of did it badly here, but you have to remember that one. Yeah, I can kind of get them both visible for a second at least. We're not going to worry about that one anymore because it doesn't actually do anything, as we said. I'm going to take that one, though, and I'm going to just modify it slightly, well, seemingly slightly, by saying it's going to be equal to, I won't bother with I guess I can put an F2 at the end here, might as well. F2 times W of, well, let's start from the beginning actually. We take W, multiply W1, multiply X, add B1, but then instead of just multiplying that by W2, we actually apply a nonlinear function now. So I apply some function, which I'm calling F1. F1 is going to be actually applied element-wise. So whereas this is a vector in Rk, but I'm going to apply this nonlinear function to all of the entries. And I'm going to do this again. I'm going to now multiply this sort of the result of this function by W2 and add B2. And then if I want, apply another nonlinear function at the end, though actually the last layer can just be linear if you want it to be. And you can actually pick a whole bunch of possible nonlinear functions here. So very common choices for nonlinear functions are the tan h function. This is e to the 2x minus 1 over e to the 2x plus 1. The form doesn't really matter. What really kind of matters is that this is a function that varies between -1 and +1. And as you go real negative, it goes to -1. As you go real positive, it goes to +1. But in both directions, it saturates. So it looks like a kind of an S. A very similar function, but a different one, is called the sigmoid function, which we actually saw a little bit in logistic regression, or we actually didn't see it. I think we didn't actually see it that way, but it's actually underlies some of the things like logistic regression as well. But the point, for our sake here, is it's just a nonlinear function that this time varies between 0 and 1. So not -1 and 1, but 0 and 1. Actually kind of one that seems sort of silly, but ends up being by far the most popular and common form of nonlinear function, is something called a rectified linear unit. That's just the maximum of 0 and x. So we just take our linear function and clip it at 0. And the cool thing is, if you do that, if you apply a nonlinear function in between these layers, even something like the rectified linear unit, all of a sudden your architecture can no longer be represented by a linear function anymore. So it now actually, you do gain representational power over your old network. And in fact, though I won't show it here, it turns out that for a large enough value of k, in other words, a big enough sort of number of outputs of this first operation here, this network, so just without the linear one in the end even, this network with any of those functions is capable of representing any function. So it's actually a very cool result. Now you have to, that's sort of the same way that polynomials can represent any function, right? You need a lot of them, and it's sort of a silly way that they kind of overfit to the data to do it, but you still actually can represent any function by what's called a 2-layer or a 1 hidden layer neural network. I've kind of mucked up that drawing there, but it doesn't matter if you have that second nonlinear function or not actually for that result. So the way that we draw these things is like this. In fact, we'll oftentimes leave out the individual stuff there and just draw sort of layers as individual stacks. But we can kind of think of this as the first layer is our raw inputs. So it's our inputs from and this, I should say that this is a single example. So this is on a single x superscript I. But I'm leaving out the superscripts just because we don't need it. But for a single example, where x1 here maybe is my temperature and x2 is the day of the week or something like that, what we do is we take those inputs, we multiply them by the linear transform W1 and B1, and then we apply a nonlinear transform to get our first set of hidden units. And these ZIs are called sometimes the hidden layer or activations. So we actually have a name for this whole thing. Because it gets tedious to kind of write these things composed one after the other, especially when you have a lot of layers, I'm going to call this Z2 in this case. Or do I call it? Well, sorry, I'll just call it Z for now. This is going to be my hidden layer. We'll soon talk about subscripts on those things. And then we form a linear combination of the hidden layer to predict the actual output. And so you may see figures like this. This is just sort of saying that we take the first layer, where we have a fully connected network to get to the second layer, and then we have a fully connected network to get to the last output of our prediction of our network. I probably should have an H theta there of x instead of y, but you get the basic idea. And again, the important point for this slide is that these terms Z are called they're often called the hidden layer, or sometimes the activations. The term activation comes from the nomenclature around the neural part of neural networks. But essentially, what's interesting about them is that these are the learned features of our algorithm. So there's nothing in the data itself that says what these things should be, right? We don't actually have any sort of loss function that measures the difference between this term and something else in our data, right? They can be whatever they want. They can take on whatever values they want to take on in order to actually output good predictions in the end. And so because of that, they're called a hidden layer or an unobserved layer sometimes too. But the point is they don't have to do anything necessarily, and what they do is just sort of incidental to achieve the ultimate goals of the actual total network. So a few sort of interesting properties here. So as I mentioned, I highlighted this before a little bit, but one point is that a neural network, yeah, sorry, question.
So it sounds like the neural networks are defined as alternating between linear and nonlinear layers.
Yeah.
So why do we do that? Why not just do all nonlinear, or do linear, linear, nonlinear, linear, linear, some other thing?
I see. So the question is, why don't you sort of compose them in some other way? Because neural networks, though there are different linear operators that are used sometimes, for the most part, they are definitely sort of this linear, nonlinear. There are, I should get back a little bit, there are some architectures that are a little bit more complex than this that sort of have very specific nonlinear combinations together, but this is by far the most common kind of formulation. And the reason is a few things. So if I have two element-wise nonlinear functions applied after the other, I can often just incorporate that into one nonlinear function, right? If they're element-wise and everything like that. If they're not element-wise, then the space of all possible nonlinear, non-element, joint functions just gets really big, and it's unclear how you even represent that, right? The nice thing about linear operators is that they are it should be obvious actually why we don't do two linear in a row, right? Then we have that same problem up there. So we don't ever do two linear in a row. Two nonlinear in a row, if they're both element-wise, they can just be usually combined into one more complex but better description of a nonlinear operator. And then if you sort of have, well, why don't we have multiple nonlinear that are sort of composed of joint functions? Well, that function space is really complex and not very nice and smooth. And so it's actually kind of hard to optimize sometimes and hard to even know how you would define functions in that space. So it's by far more common to just have this structure. And because of this properties like universal function approximation, you don't really lose much by sticking with this fairly simple structure. I should add that there are more complex architectures, but they typically still do follow a form that looks something like this. Yeah.
So for the nonlinear functions, can you give some intuition as to why we choose those nonlinear functions?
Why do we choose these nonlinear functions as opposed to other ones? No, I can't give any intuition why. Historically, there's functions people tend to use. The sigmoid functions are smooth, so they can be optimized easily. And then the tanh is just kind of a version of that varies between -1 and 1 instead of 0 and 1.
Infinitely many smooth functions.
Infinitely many smooth functions. We can really choose anything we want. They're monotonic, which has some nice properties too. If they're not monotonic, then you have this weird thing where you sort of, as you get more weight on a particular element in one thing, you get reversing effects, which seems kind of odd. So monotonicity is nice as a nice property of all of these things. And then the problem, the reason why the ReLUs became so popular, or there's a lot of reasons actually, but one reason why they are so popular is that one of the problems with the sigmoid and tanh functions is that as you get really, really positive or really, really negative, the derivatives there go to 0. So even though, over here you may be really far from the correct answer, your derivative is actually 0, whereas the rectified linear unit doesn't have that problem. Its derivative in the positive portion, at least, is always 1. So they're largely ad hoc, to be honest. There are some reasons, there are some results about representational properties of different types of units, but the real story is that they're intuitive what these things are doing, the ranges that they output. They seem to work pretty well in a lot of cases, and it doesn't seem like anything else we do works any better. So that's why they are the ones that people use.
That people try out.
Yeah, and so right now there's a lot of work on sort of modifications of these ReLUs that are smoothed versions of them or versions that have some slope on the negative part. There's a lot of those things are going on right now, but it's very inconclusive to see. The ReLU advantage over other ones was definite. This is definitely an advantage. Some of the other things, it's much less clear what's sort of going on. And because it's really hard to sort of give any theory about these things, there's nothing to do other than just try them on a lot of architectures, and so it's sort of a, finding new nonlinear functions is not that, I don't think it's that interesting a topic, though there are some cases where people have come up with cool new ideas there. Anything else? Yeah.
Yeah. So if one layer of neural networks can represent any function, why we are doing a several?
Yeah. So I'll get back to that in a second, actually. So a few more notes. So first of all, they are universal function approximators, but this fact is actually not that relevant. Everyone mentions it as a great fact of them. It's not actually that important. So polynomials are also universal function approximators, right? We can represent any function, namely, as long as we have our degree of our function as large as the number of points and they're all distinct, we can represent any function with a polynomial too. So they're also a universal function approximator. Actually, any class with infinite VC dimension is going to be a universal function approximator. So there's lots of these things. What really matters is sort of how you trade off between function approximation and complexity of the underlying function. And it seems like neural networks fill a good kind of sweet spot in that regime. And that they if you add enough parameters, they really can represent any function. But for a fixed set of parameters, they seem, at least empirically, to be able to represent a good set of functions. Again, this is oftentimes when you use specialized architectures like convolutional architectures or recurrent architectures, which we'll talk about 2 lectures from now. So just to sort of clarify a few more things here, these functions are no longer convex in their parameters. So in attaining this additional representational power, we have thrown out convexity. Even that one there, the linear one, is not convex in its parameters. So actually you can't find that optimal solution, even though you can just reduce it to a linear function and then solve it. You actually can't find, or certain techniques at least won't be able to find that one. So we've thrown out convexity. I'll talk in a second about how we still go about solving these things, but we're giving up on convexity. And so part of this now is that there actually is much more space for different architectural choices that really matter, right? Because we can't find global optima anymore of these functions. And so the choice of how we design our network and how we optimize it actually does affect how good of a solution we get. So there's a lot more kind of freedom and a lot more uncertainty also in kind of how we choose these things. So this is both a positive and a negative, I guess, depending on what kind of research you like doing in machine learning. But I'll just throw out one more term here, which is deep learning, because this is sort of the term that we're using our lecture to describe, or we're just using to describe our lecture. And deep learning in this context is just neural networks with multiple hidden layers. There's no exact number that you need before you become deep versus shallow. But the general idea is that when you do deep learning, you're talking about compositional architectures that have multiple nonlinear units and linear transformations in them. So the way we will write this is we will write as a recurrence where we say that zi plus 1. And here now actually zi itself, each zi is going to be a vector. So now the I is not a subscript into the vector, is now actually a vector itself. Apologies for this notation. We just run out of subscripts to use, and we very rarely actually need to index into a particular hidden unit. So I'm going to use now subscripts on the hidden units to talk about what layer they're in. But the recurrence of a neural network is that zi plus 1 equals our function applied to some linear operator times, where's my eraser? Oh, there it is. Times the previous hidden layer plus some bias term, where our first hidden layer is the input to the Z1 is the input, and our hypothesis function is equal to just the last one, if there are, say, k layers now in our network. Yeah?
It looks like the number of nodes in each hidden layer is like the power set of the previous hidden layer, or like every combination is going into one node. Is that true?
No. So these things can be whatever sizes you want. So the size of each layer is only determined by the sizes of the matrices there. So because we're applying this thing element-wise, this thing doesn't change the size of it. So if this, let's say this vector here, and I'm going to use let's say the hidden layer is RP, right? It's an RP, so it has P units in that hidden layer. And this matrix here is something like R Q by P, then this one would just have Q units in it. So there's no necessity of the size here. It's just the only size that's determined is by whatever size you set as your matrices.
So those arrows don't really, I mean,
The arrows there correspond to the fact that every output can have some, every element in the previous layer can have some influence on the output in the next layer.
so there's like an arrow from every node in this.
Yeah, and that corresponds to a dense W essentially. So W is a dense matrix. That means that every node can have an impact on every other node in the next layer. That corresponds to W being a dense matrix.
So each like one of those circles is essentially like was like one of the parameters, I guess, or so to speak, or one of the inputs.
Like
Like on the initial one, Z1 is equal to X, right? Each is a circle.
Yes, in the initial one, each sort of circle there is a single coordinate in the input vector.
Right, and then
In the middle,
transformer was W, you get like a new set of.
yeah, but the very important, they're not parameters. The parameters are the W matrices. Those are the hidden layers. And so each circle there would be an entry in a hidden layer. Yeah.
Is there a particular reason you don't, so you start with a linear transformation and then a nonlinear and linear nonlinear?
Yeah.
Why can't you start with a nonlinear and then is there something?
Again, you could always capture that by just having the first one be the identity matrix, and then you've done that. So it's just not worth sort of differentiating. Yeah. Yeah.
So are you using different nonlinear
You can. It's common because especially with a densely connected network, it's common just to have the same one. Oftentimes the ReLU, and the last layer is then linear. Oftentimes, but you can if you want to. There's nothing preventing you from doing that. I have notation of different ones just because the last one is often just purely linear. There's no nonlinear function at all, so it's good to think about them being different. Okay, so now the question that was asked before is why should we use deep networks over anything else? If in fact a two-layer network or one hidden layer network is a universal function approximator, why should we go ahead and bother with these deep architectures? So there's actually a couple of motivations for why we might want to do this. So the first one actually comes from circuit theory. So there are a lot of functions, actually, it turns out, that can be solved efficiently with a multi-layer circuit that can't be solved with sort of a two-layer circuit. So for example, computing the parity of a bit string. If we need to compute that in a single layer neural network, or single hidden layer neural network, the size of the hidden layer would actually have to be 2 to the n. Parity is just you count the number of is the number of ones, even or odd, in some bit string. To actually compute that function with a single hidden layer network would take a hidden layer size of 2 to the n. You basically have to encode all possible parity strings and just then select the one that, or all possible strings and select the actual one that it is, and then output that string's parity. So that doesn't very good. In contrast, actually, if you're willing to use a logarithmic sized network, then it's actually trivial to compute the parity function with a much smaller network, because you basically just have a like tournament network where you just have two nodes that then leads one node in the next layer that is like the XOR function essentially, and you can compute that very efficiently with then order n total hidden units instead of order 2 to the n hidden units. So that's a great example. Actually, does that, I mean, again, sort of very fuzzy here, but does that example kind of make sense? Basically, if I have some network here, I want to know if there's an even or odd number of ones here. What I do is I sort of make an XOR function here, an XOR function here, an XOR function here, and that'll give me the parity. Whereas if I actually have to do it with, well, this is a bad example, but if I have to do that with for a much bigger string with only a single hidden layer, I can't do this actually. I have to basically encode all my inputs to one thing that says is this, for all those inputs, is that even or odd? I have to have one for every possible combination here that sort of maps every possible state of the of the network. So that seems kind of bad. That seems wasteful. Let's use deep networks. But what's really unclear, actually, I should add, and I don't want to dwell too much on this because this is sort of a nice theoretical example, but it's also kind of trivial. And the bigger point is it's very unclear if we learn anything like that at all with real neural networks. It's just there isn't a very common function to learn. We typically don't learn functions that are like the XOR, even on a single layer, that are non-monotonic. So it seems very odd to know, is that really something we should use as a motivating example or not? So that's sort of nice from a theoretical standpoint, or at least maybe a theoretical standpoint, but it's really unclear if that has any real bearing on how these things really perform. The second one is the motivation from biology, which is sort of maybe made very explicit by the name neural network, which again, if you write it this way, doesn't look very brain-like, right? But again, with the naming conventions in machine learning, we are very good at coming up with cool-sounding names for things, and neural networks is a great sort of marketing ploy because it makes things seem like they are intelligent and like the brain. So you know, the analog here is that we don't know much about the brain, but we do know that it uses multiple layers of neuron connections to make decisions or to make inferences about the world. And so maybe we want to do that also in our. Therefore, we have an existence proof of some architecture that's deep, and so we want to emulate that. And the danger here is to assume that there really is too much connection between neural networks as they are in sort of the representational sense and the actual brain. We know very little about the brain. We know some things about sort of how individual neurons work, but the overall workings of the brain are still really unknown to us. And we do know, however, that it looks nothing like that, the brain, right? So whatever the brain is doing is much more complex, the activations, than simple things like these linear composed nonlinear functions. There's all sorts of timing and kind of spiking effects and things like this that are not at all modeled here. And so it's a very weak analogy, I think, to say that the brain's like that, therefore we also want to do it. When really we're just talking about a mathematical construct here versus something we don't really understand in the brain. And so what it finally comes down to is just sort of the empirical argument, which is to say, in a lot of domains, we try them both. We try an equal number of parameters with a single hidden layer, or we try the same number of parameters with smaller but a deep network, and the deep one appears to work better. So that's why we do it in practice, especially, I should say, when you have things like convolutional structure or some other structure in your deepness. They appear to work much, much better than anything we could do with a single layer. With a single layer. Yeah. So.
Can you give some indication behind how much expressivity of the function is added with each hidden layer?
Not in a formal sense. So there actually is some work in VC dimension properties of neural networks, and I believe that you can show the expressivity increases exponentially in the number of layers you add. So it increases exponentially with the dimension d, whereas it only will increase linearly when you add more to a layer. But again, that's assuming very unrealistic architectures like the XOR function. So most arguments you can give in terms of the theoretical representation power relate to functions that we don't actually learn in practice. So that's sort of the problem there, kind of the missing link there is that this is an obvious case, right, where the representational power increases exponentially in the number of layers and only linearly in the number of hidden units in a single layer, but it's not that useful because we're not actually learning functions like that. So you can go the theoretical route, but it doesn't really tell you. That's much more like circuit theory than it is actually talking about neural networks.
Well, we have overlaying problems like overfitting. Too many layers.
Yeah, so the question is, are there things like overfitting that still happen? And yes, absolutely. So as you have more functional representational power, your chances of overfitting do in fact grow. What's actually kind of amazing though is that it doesn't seem, with these architectures, at least the ones we have, it doesn't seem to be as bad as you might think. So essentially we can come up with architectures that seem, in theory, have a ton of parameters that could completely overfit any function, yet they also perform pretty well both on the training set and the validation set.
You mean those Fi and Wi are the same or they change?
Sorry, I'm not talking about the Fi and Wi here. I'm just talking about the, sorry, I'm missing that question. It doesn't really relate, the overfitting doesn't really relate to the Wi's or Fi's here.
You said there are more parameters.
Yeah, because in a neural network, so if you have a linear function, right, I only have sort of the number of parameters equal to the number of total inputs. Whereas if I have this, I have way more parameters, right? I have, in my first layer, I can create however many features I want. That's essentially that number of parameters for each hidden unit in the next layer. And then I have that many more next time. So I have many, many more, much higher dimensionality to my parameter space than I had just my W's and B's. Not the F's so much, because those aren't really parameters that you tune. Those are just fixed in the architecture. The W's and B's are much higher dimensional than just the theta we had before, but yet it seems to work a lot better. Yeah.
Is there some heuristic to choose the dimension of WIs?
No, but the reality is the other thing that's cool is it doesn't really appear to matter that much. As long as you have them sort of large enough, you pick them as big as you want, as big as you can compute, and then you use some other techniques to prevent overfitting. And it works pretty well. What was that?
Is it sparse?
No, W is dense here in these cases. We'll talk about convolutions too, but in the fully connected case, W is always assumed to be dense. Yeah. Okay, so let me pause a little bit now and kind of go back to my original question, which is why is this all happening right now? This math was known at least in the 80s, probably much earlier than that, but at least in the 80s, you could have read the same equations on the board and people would have understood them and known them well. So why is this all happening right now? I don't think it's a matter just of these things, we just need to work a little harder. We just didn't know we were working the wrong things, and so it didn't work. I think something's actually changed. Something's come together, John, to make these things, to make now the right time for these things. And I like to sort of just highlight the fact that I think there are 3 causes that are really contributing to what's happening right now in deep learning. So the first is that, well, it doesn't really matter how you order them actually, because they're all necessary for this thing to work. The first thing is that we have lots of data. So that's the bottom right quadrant here, or bottom right point here. When you have only a few, and this is sort of what we saw by motivating it by the example of VC dimension last time. If you only have a small amount of data, if your M is very small, there's only a limited set of function classes you can actually learn, right? Because as your class gets more complex, as the VC dimension goes higher, you need bigger amounts of data. So finally, we are actually getting that large amount of data. The other thing we have is that we have these high capacity models. In other words, we have models with high VC dimension. We've kind of developed this suite of models that works pretty well, that both has high VC dimension, but also sort of in practice doesn't appear to overfit that badly. But the need for VC dimensions, or for a reasonable VC dimension here, is very real, because if we just had lots of data and fed it into a linear classifier, it wouldn't actually matter, right? The flip side of VC dimension is that for a fixed VC dimension, once you have more than the certain bound on M, it doesn't really help things to get even more data, right? Adding more data doesn't really help. So we have this sort of well-established class now of high-capacity models that allow us to actually make use of all the data that we are generating. And the last thing that we have is that we have, finally, in some sense, the computing power to keep up with all of this. So the advances in things like GPU technology, which is sort of incidental, it was developed so people could play games that look more realistic, but it sort of took off in the context of deep learning because people found out you could do linear algebra, which, by the way, underlies all of this, really fast on a GPU. It happens to also be good, you need linear algebra for drawing realistic shadows and textures and stuff like that too, so you can tend to use them also for computing these neural networks. And the analogy, I think, this is obviously kind of maybe silly for a class like this where we're actually getting into technical details, but if you wanted to describe this to someone who's a little less technical maybe, I like the analogy of an airplane for this, like a jet plane. So the high capacity models are something like the design, the aerodynamic design of the airplane, right? If you attach the data is the fuel for the airplane, and the computing power is like the engines on the airplane, right? So if you don't have one of these terms, one of these things don't really work very well, right? If you have lots of jet fuel, but not much, and a big engine, but you attach it on a big brick building, it won't go very far. You can't actually transform that to useful work. If you have, an airplane with jet engines and nice aerodynamic design, but no fuel, you're not going to go very far. And finally, if you leave off the engines, you probably aren't going to go anywhere either. I think it's actually a reasonable analogy for what's happening here. Is you need all these 3 things coming together in order to take your data, to use the computing power, and use it together to accomplish actual meaningful work. So If you want to describe what's big about deep learning to people recently, I like the airplane example. Okay, any questions now before I jump into a little bit more detail about how we're going to go ahead and actually learn these models? Okay. So let's talk now about the last point. And we're not going to get through this today. This is actually mainly material for next time. But let's talk a little bit about training neural networks. So again, the nice thing about this, the nice thing about what we've sort of done so far in class is that neural networks in the context of machine learning are no different really from any other machine learning algorithm. In that, our problem we want to try to solve is the same optimization problem we've been talking about the whole time. In other words, it's to minimize over theta. That's now all the weights and biases of our network. Usually not the functions themselves. We treat those as kind of fixed, but the weights and the biases. The sum from I equals 1 to m. Now this is over our different examples we have in our data set of the loss of our hypothesis function on the ith example and its class. And this loss function, by the way, can be the exact same thing we use for linear classifiers. So like logistic loss or hinge loss is very reasonable to use there. If you have a binary classification task, if you have a regression task, you can use things like squared loss or absolute loss. Now again, this is not a convex problem because our hypothesis function is not a convex function of the parameters, and when you compose the loss function, it's still definitely not convex. So this is not going to be a convex function in theta, which are all our weights and biases. However, we're just going to kind of ignore that, and we're going to be satisfied with finding local solutions. So we're going to be okay if we don't find the globally optimal solution for all our parameters. We're going to be okay with a point that's just kind of locally optimal. And the way we're going to solve that ends up being exactly the same way we solve a lot of machine learning algorithms, which is just via gradient descent. So we're just going to use our same gradient descent technique to actually try to find a good point. Now gradient descent, again, will not find the globally optimal solution in a non-convex problem, but it can still find locally optimal solutions, right? The gradients still point in a downhill direction in the current function. So if we just follow the gradient, we'll reach a point that's better than our current point. Again, that proof didn't have anything to do with the convexity of the problem. Convexity only implied that we find the global optimum. So we can use gradient descent to optimize our function just like we did before. It turns out, however, that we actually use a slightly different thing called stochastic gradient descent, which I'll describe now, which ends up being a slightly better idea for sort of reasons that become obvious as you look into it, about a better thing to do than traditional gradient descent on that problem. So let's think about what's the challenge of gradient descent, of running gradient descent to solve this problem. So let's say I want to compute my gradient with respect to lambda. And I guess when I write this now, what I really mean is like the set of all gradients with respect to all my parameters of this thing. But let's compute the gradient of this thing, of my loss, and yi. Right, this is, we know that the gradient's a linear operator, so we can move it within the sum. So this is equal to the same thing as the sum from I equals 1 to m of the gradient with respect to I of L h theta xi yi. So let's consider what we have to do to compute this gradient then. And then we make the updates, by subtracting a small amount from our current parameters of this gradient here. So to compute this gradient then, this whole gradient here, that requires that I sort of look at each example in my training set and compute the gradient with respect to that example. So I take all those gradients, I add them up together, or maybe average them if I'm talking about an average loss here. And that's my total gradient over my entire training set. So that seems like a good idea, but it also seems kind of wasteful, right? Because if you think about the complexity of computing this gradient now, this will require, I I actually don't even care how much this gradient costs, but we know that however much it costs to compute this gradient here, I'll say it costs time t to compute that gradient, it's going to take time t times m, where m is the number of training points, and say it takes O of t here. it's going to take O of t times m to compute the whole gradient, which is to say that we're doing m times that much work. And again, what I just said here is that these models are really good when we have lots of data. That means m is going to be really big. It's going to be in the thousands, hundreds of thousands, millions even sometimes. That would not really, that would not really cut it to have to wait, compute a million gradients, even forgetting how complex it is to compute these things, which is somewhat complex, as we'll see in a second. Even forgetting that, it just would not really work. So what people do instead is something called stochastic gradient descent. And I'm going to describe it from a very sort of high and practical level, not a formal level here. But the idea is that in some sense, what you're doing when you compute a gradient is you're taking all these different gradients, or the total gradient, taking all these different gradients, and you're just averaging them together. I mean, you're also summing them, but it doesn't really matter. You can always just divide by m here. So just say, like, this is our loss function, really. So our true gradient is just the average of all of these. So you're taking them, you're averaging them together. Well, it seems like, even if we just took maybe a few of these, or maybe even in the extreme case, we just take one of them, then we're still going to get a quantity, a single gradient here, which in expectation points in the same direction as their average, right? It's just that for any given example, it might be far away, but an expectation, it'll be kind of the right way. So what we're going to do instead in the stochastic gradient method is we're going to take a bunch of maybe smaller steps in these gradients with respect to each individual, or with respect to the parameters of each individual example, and hope that over time, that will actually lead us to a similar position in our state space as the overall gradient. So the stochastic, I'll just put them both on this slide here because this will kind of highlight the difference here, is that with gradient descent, you kind of have this very expensive inner loop before you can ever update your parameters. So gradient descent says the algorithm is to repeat to first, I guess I should probably so I guess the way I wrote it was for I is 1 to n, to m. I'm going to set this gi term. Gi's are going to refer to gradients here. They're like gradients, but not quite like that in the later slides. So this is just this slide that they refer to gradients. This is going to be equal to the gradient with respect to the ith example. Gradient with respect to the parameters on the loss evaluated at the ith example. Right, so you compute this whole thing, and then when you're done, you update theta to be equal to, set equal to theta minus alpha times the sum, or maybe the average of all these things. So that's kind of computationally how you would implement gradient descent. Now, the stochastic gradient descent algorithm, on the other hand, is maybe I kind of ran out of space there. Let's try to do this. So SGD, stochastic gradient descent, seems simpler. You repeat the following. You just pick some i. Typically, you cycle through all the i's, though in theory, actually, you could just pick one randomly each time. That would be fine, too. And I just take my gradient on that one example and update my parameters based upon that. So theta is equal to theta minus alpha times the gradient on that one example. LH theta xi. And so, again, in practice, what you really do is you sort of cycle through all your examples 1 to m usually, and you repeat the whole process. So, I both iterate over my data set multiple times, but each time I have the parameters based upon just one gradient step. Yeah.
Do you assume like a bounded gradient difference with respect to different samples so as to get a high concentration?
Can you repeat that question again?
So I mean, in expectation, you
Yes.
But do you want to get a high concentration?
I mean, so the question is sort of about the variance kind of that estimate, right? So the question, I mean, for the purposes of this discussion, we're not going to get into the actual variance estimates. I mean, this will converge no matter what, because the expectation is right as long as you have, bounded examples and gradients that are not actually infinite, which they won't be if you have a bounded set and you have parameters that are not infinite here. Let's see. So in practice, we're not really concerned about sort of the theoretical convergence of this thing. We're just concerned about the practical convergence. And in practice, you just sort of pick an alpha that's usually a little bit smaller because you have more noise now. So you want to pick a smaller alpha for this for the first one, but it works and all the bandedness properties work fine. Theoretically, yes, it'll converge slower when you have a variance. The convergence depends on the variance term of these estimates, but we're not going to worry about that right now. Yeah.
For the stochastic gradient reason, does it ever happen that theta reaches a local minimum, local optimum before I goes from 1 to m, like before all the examples have been used?
Yeah, so this actually, the question was could theta reach a local optimum before it does that? And so yes. I mean, think about the case where m is actually infinite here. So it's perfectly reasonable to apply SGD to the case where you have an infinite number of examples. And actually, there are some domains where, for all intents and purposes, you have an infinite number of examples. You never repeat your examples. You just keep going, on your incoming stream of data as much as you want. Now, there's also something interesting that happens here, which I'm not getting into really, but stochastic gradient descent actually can help you avoid some types of local optimum too. And the reason is because there's a noisiness to these gradients, you actually sometimes can kind of get a little bit out. You're sort of not going only in one direction, so you actually can kind of sneak out sometimes of these local optima and actually do better than you would and avoid local optima that you might get into were you doing normal gradient descent. So the answer is yes, but there's also even more ways in which SGD relates to things like local optimum. Though that's not really true in theory. And in theory, in expectation, you get stuck in the same thing. You also have to do things like decrease the step size, decrease your step size by using a certain rule if you want to converge exactly. But in practice, you just fix it at some reasonable number and hope that it converges and lower it or raise it as you need to. Yeah.
What kind of a loss function do we generally use?
The loss functions used are the exact same ones used for classification or in a linear setting. So very common to use logistic loss for binary cases, very common to use square loss for the regression case. For the multivariate classification case, you use a multivariate version of the logistic loss. But those are the most common ones, but you can use whatever you want. Just use the same. Hinge loss you also use very often, yeah. Yeah.
Same question, like whether it can, if you use SGD, whether it would converge to the optimum before m. So wouldn't it depend on the type of sample that you have? If your samples don't represent the entire space well enough, you would never have a particular gradient and you would never
I see.
optimize in that particular
Yeah, so
direction.
So the question was sort of, does the type of samples affect the convergence? Yeah. So we're assuming through all of this that the samples are IID. So that was sort of the assumption in the theory. Virtually any machine learning algorithm, if your samples are biased in one set, you're not going to reach the true optimum. And so if you have all of one type of examples, in the first million, and then the next one you have in the next million, and you effectively converge in the first million, then yes, you have those problems. But we're going to assume that these essentially are independent, or you shuffle them if they're not independent and stuff like that. Okay, so now let me just pause here because this is actually a good stopping point for the next class, and just say that the question now is, of course, how do I compute these gradients? Right. So I reduced everything to sort of compute a gradient on a single example. How do I actually compute the gradient on that single example? What do I actually do to? It seems when I have these multiple composed functions, even though we know how to take derivatives, it sure seems pretty complex to do so, right? If I start writing these things out, they very quickly fill up pages of notebook text, right? We don't want to do that every time we want to develop a new architecture. So how do we actually solve these gradients? And it turns out it's a very elegant way of doing this, which again goes by many names. Reverse mode differentiation is actually the name that it sort of was first talked about under. But in the context of neural networks, it's called the backpropagation algorithm. And so next time we'll discuss what backprop is, how it works, and some basic properties of this algorithm.